This slide shows some benchmark acidity constants, or pKa values, for molecules with relevance to organic chemistry. And we can use these pKa values directly for quantitative comparisons of acidity with a conceptual understanding of what the pKa value represents. For example, the most acidic compound on the table is sulfuric acid in the top left, with the most negative pKa value, indicating that Ka has the largest value in the table for sulfuric acid. On the other side of the table, the least acidic compound is ethane. With a pKa of 50, that Ka value is 10 to the negative 50 power. So in general here, when you're comparing pKa values, the more positive the pKa value, the less acidic is the compound, and the more negative or less positive the pKa value, the more acidic is the compound. So these tables go from least acidic in the bottom right, with increasing acidity this way, and then increasing acidity this way, to most acidic in the top left. And this is one way we use pKa values. Thanks to the conjugate seesaw, we can also use pKa values to compare the basicity of two conjugate bases of acids whose pKa's we know. And we're going to do that on this slide, answering the question, which is the stronger base? Benzene sulfonate, the structure of which is right here, or but-3-ene 2-ide, this allylic anion, whose structure is right here. Now, both of these are negatively charged, and to think about generating the conjugate acid for a pKa comparison, let's add a proton to the negatively charged atom. So there's a lone pair at each of these negatively charged atoms. We can protonate that lone pair, add H+ to it, right? And that gets us to the conjugate acids on the right, benzene sulfonic acid and but-1-ene, this compound right here, this terminal alkene. And we can look up their pKa values. Benzene sulfonic acid has an acidity constant of -2.8, and butene has an acidity constant of 35, specifically at this position where the negative charge was located here. That's a particularly special position because this is a resonance stabilized anion, which is an interesting observation that we would use if we were comparing these two anions qualitatively. But for the moment, we're thinking about the quantitative approach in pKa values. So now let's think about what the pKa values are telling us. Well, they're telling us that benzene sulfonic acid is actually a strong acid. Its pKa is negative, right? It's more acidic than hydronium ion with a pKa of 0. And so this is a strong acid. On the other side of the coin, the very high pKa value for butene means that this is a very weak acid. So now we've compared the acidities of the acids, we can apply the conjugate seesaw to reason about the conjugate bases. If benzene sulfonic acid is a very strong acid, that means benzene sulfonate is a very weak base. On the other hand, if but-1-ene is a very weak acid, that means that this allylic anion, the conjugate base, is a very strong base. And so the weaker base here is benzene sulfonate, and the stronger base is the allylic anion here. And it's all based on this seesaw idea. In the first case, HA is a strong acid. It's the heavy end of the seesaw, if you like. This makes A- the lighter end of the seesaw and makes A- a relatively weak base. On the other side of the coin, we've got a pretty strong A- in the case of this allylic anion, and so the conjugate acid HA is the high end of the seesaw and is relatively weak. So notice also that we didn't really have much to say about these anions. We made some qualitative observations like resonance stabilization, that kind of thing, but we went right to the Ka's of the conjugate acids. And so here, drawing in the conjugate acid structure was critical, recognizing, okay, where's that negative charge? And when I add a proton, where does that proton go? What's the structure of the resulting conjugate acid? And what's the pKa at that position? And this is something that you would look up, right? You would look up this number in a pKa table. Let's do another example, using the pKa benchmarks that we've already seen to identify which of the following anions is a stronger base. So we're going to be using the conjugate seesaw because we're going to need to use pKa values to reason about basicity. And so the first thing we want to do is consider and draw and think about the conjugate acids protonating putting a proton on each of these bases to generate the conjugate acid. So how do we do that? Well, find the anionic center, draw in the lone pair there, and essentially add the proton to that lone pair. So in this first case, we go from this acetylide anion with negative charge and an sp hybridized carbon to this neutral conjugate acid. And in the second case, well, that nitrogen has a couple of lone pairs actually, and one of those can be protonated. This gets us to NH3. Ammonia is the conjugate acid of this anion right here. Okay, now I've highlighted these protons that we just put on. What we want to do now is look up pKa's for these particular protons that we just put on the conjugate bases. The pKa of this proton is about 25. The pKa of the proton in NH3 is about 35. And if we think conceptually about pKa here, this means that the weaker acid is NH3, and the stronger acid is this compound, which is acetylene or ethyne. So with this as the stronger acid, that means this is the weaker base. The conjugate base is the weaker of the pair. On the other hand, with this as the weaker acid, that makes this anion the stronger base of the two bases we've considered, right? Applying the conjugate seesaw again, if this acid is stronger than this acid, then logically, according to the conjugate seesaw, this conjugate base must be stronger than this conjugate base. We've just seen how you can use pKa and pKb values and the conjugate seesaw to think about relative acidity and basicity. You can also use pKa values to predict the favored side of a given acid-base equilibrium. So if we had a general acid-base equilibrium between an acid HA and a base B-, not necessarily involving water or even a solvent, we can determine K for this reaction if we know the Ka values of HA, the reactant acid, and HB, the product acid, or sometimes you'll hear this referred to as the conjugate acid. The idea here, and this falls out of the math of the reaction quotients and the equilibrium constants, pK for this acid-base reaction is the pKa of the reactant acid, which is HA, minus the pKa of the product acid, which is HB. Now, pK is just like pKa, it's an equilibrium constant. And so the more negative it is, the more product favored the reaction is. Negative pK indicates that the equilibrium constant is greater than 1 and that at equilibrium the products are favored, or the reaction is favored in the forward direction. Positive pK indicates that the equilibrium constant is less than 1, such that the reactants are favored at equilibrium, or the reaction runs in reverse spontaneously. You may have heard it back in introductory chemistry. Now, qualitatively here, one thing that also falls out of the math and that we can notice, and that's a very useful practical rule, is that the side with the weaker acid is the thermodynamically favored side. And this, again, falls out of the math of pK. If HB is the weaker acid, then this difference will end up being negative. If HA is the weaker acid, then this difference will end up being positive, and the reactants will be favored in that case. So let's apply this with a quick example here. So here I've got tert butoxide anion reacting with water to give tert butanol, notice that's the conjugate acid of this, and hydroxide, which is the conjugate base of water. So the two pKa's are given, pKa for the reactant acid, pKa for the product acid. And we can notice just from inspection of the pKa values conceptually, tert butanol is a weaker acid than water. And so as the weaker acid of these two, the favored side will be the one with tert butanol on it, the product side. And if we calculate the pK here as the pKa of the reactant acid minus the pKa of the product acid, well, that's 14. That's the pKa of water minus 18, which is the pKa of tert butanol. That's -4, indicating a product-favored equilibrium in this acid-base reaction. Now, you should notice that we drew this with reversible reaction arrows because this pK at about -4, 10 to the 4th power is the value of K. It's marginally reversible. The forward and reverse reactions are both worth paying attention to. But when pK is very, very positive or very, very negative, we can think of the reaction essentially as irreversible. in one direction or another. In other words, it goes to completion. There is no back reaction of the conjugates to reform the original acid and base. So here, for example, we have an insane difference in pKa, with the product acid much, much, much weaker than the reactant acid. Because of the huge pKa difference here, this reaction goes to completion in the forward direction. And I would say that the first example we looked at is kind of a marginal case, where the reverse reaction is a little bit important to consider. And as a general guideline, no hard cutoffs. You don't want to use this as a hard kind of draconian cutoff. But as a general rule, when this difference between the reactant and product acid pKa's is less than about -5, this is a good kind of line in the sand, so to speak, the reaction can be considered to go to completion, go all the way to products. Now, greater than +5, as a corollary of this, is basically a negligible acid-base reaction in the forward direction. The reactants are so favored that the reaction doesn't go forward at all. That's an important corollary of this idea right here that comes about if, for example, we flipped this reaction and asked hydroxide to deprotonate butane. That is not a favorable acid-base reaction at all. Let's practice applying pKa values to predict the favored side of an acid-base equilibrium now. And we're going to look up pKa values to do this. In the next video, we're going to learn the qualitative structural approach to predicting relative acidity that's going to allow us in many cases to not have to look up pKa values, which is quite nice, and as I've alluded to multiple times, is really going to be the enduring part of this chapter. But for now, we're applying pKa values. And we want to keep in mind the weaker acid is associated with the favored side of these acid-base equilibria. So in the first case here, we have hydronium acting as an acid and protonating the oxygen of this carbonyl compound. The acid on the left is hydronium ion, its pKa is 0, and the acid on the right is this protonated carbonyl, which is in our benchmarks and has quite a negative pKa, -7.3. So this is quite an acidic species, as suggested by the positively charged oxygen atom. The weaker acid here is actually hydronium, the acid with the higher pKa. This indicates that the reactant side is favored. And so the forward reaction goes pretty much to a negligible degree here with a delta pKa, if you like, a pK for the overall reaction of 7.3. And so this reaction is going to be favored in the reverse direction, not the forward direction. What about the second case? Well, here we have hydroxide forming water. So hydroxide is acting as a base toward this dicarbonyl compound, and the dicarbonyl compound is losing a proton. And we can see that if we notice, okay, I've got 2 hydrogens linked to this carbon. In the product anion, I've lost a positive charge and I've lost a hydrogen. There's an H here, and there's a lone pair at that carbon. So this is acting as an acid and forming its conjugate base. Okay, so we've got an acid here, we've got an acid here. Well, we know the pKa of water, that's 14. The pKa of this dicarbonyl compound, specifically at this carbon, which is the most acidic carbon in the molecule, for reasons we'll discuss in the next video, has a pKa of 9. All right, so which acid is weaker? Water is actually the weaker acid here. So the favored side is the product side, and this reaction will run in the forward direction spontaneously. To quite a large extent, in fact, pretty much irreversible and complete, right? With a delta pKa of about -5, this is right kind of at our cutoff for complete irreversible acid-base reaction.